Have you ever thought about what would happen if you could just keep adding numbers together forever? It sounds like some kind of deep philosophical question, right? But believe it or not, it's one of the most fundamental ideas in all of mathematics. Today, we're going to jump in and see what actually happens when you try to sum to infinity. I mean, it just feels like that can't work, right? It's got to be impossible. How in the world can you take an endless, infinite list of numbers and have them add up to anything other than, well, infinity? This is a paradox that has tripped up some of the smartest people in history. But guess what? Today, we are going to crack this thing wide open. Okay, so let's make this real. Forget the abstract numbers for a sec and think about pizza. Imagine you eat half a pizza. Then you eat half of what's left. Then half of that tiny piece. And you just keep doing that forever. You're always adding another slice. But the big question is, does the total amount you've eaten ever go past that one single pizza? All right, to really nail this down and solve the paradox, we've got to switch gears and start talking like mathematicians. We're stepping into the world of what are called infinite series. And the cool thing is, there's this brilliant and honestly pretty intuitive tool that lets us tame these wild, endless sums. So yeah, let's get the official lingo down. This whole idea is formally called an infinite series. Don't let the name scare you. It's just a fancy way of saying we're adding up an endless list of numbers. And each number in that list, the A1, A2, A3, we just call each one a term. Okay, so here's the big problem, right? We can't actually sit there and perform an infinite number of additions. Our lives are finite. So if we can't just crunch the numbers directly, what's the plan? What's the strategy? Well, the strategy is actually pretty clever. Instead of trying to leap all the way to the end, which, spoiler alert, doesn't exist, we kind of sneak up on the answer. We'll just add a few terms, then a few more, and see where things are headed. These little baby steps, these mini sums, they have a name: partial sums. Let's actually see this in action. So our first partial sum is just the first term, 1/2. Easy. Now add the next term, 1/4. Our sum is now 3/4. Okay, add the next one, 1/8. Now we're at 7/8, then 15/16. Are you seeing the pattern here? With every single step, we are getting closer and closer and closer to the number 1, but we never quite go past it. So this whole behavior, this idea of getting infinitely closer to one specific number, like a target you never quite hit but always approach, that is the key to this whole puzzle. And you guessed it, in math, this has a very specific name. It's called convergence. When those partial sums all zero in on one single, finite number, we call that number the limit, then we say the series converges. It has an answer. Now, if the sums just shoot off to infinity, or maybe they just bounce around all over the place and never settle down, then we say the series diverges. It's one or the other. So, let's go back to our pizza problem. For that series, the limit of those partial sums is exactly 1. And there it is. That's the answer to the paradox. We can now say with total mathematical confidence that adding up an infinite number of slices of pizza equals exactly one whole pizza. The impossible is totally possible. Now, calculating partial sums will always get you there, but man, it can be slow. Luckily for us, our pizza example is a perfect showcase of a super common type of series. And this one comes with an amazing shortcut. It's called a geometric series. So what makes a series geometric? Well, it's all about a constant rhythm. You start with a number, which we call A, and then to get the next term, you multiply by the exact same number every single time. That special multiplier is called the common ratio, or just R. So with our pizza, A was 1/2, and we kept multiplying by 1/2 over and over. So R was also 1/2. And this is where it gets really, really cool. For any geometric series, its entire fate, I'm talking whether it converges or diverges, it all comes down to that one single number, the common ratio R. You don't have to mess with partial sums at all, just look at R. And this is why this stuff matters way beyond just pizza paradoxes. This is used in physics, finance, engineering, to model everything from radioactive decay to how interest on a loan works. And the rule itself, it's so simple, it's beautiful. Check this out. If the absolute value of R is less than 1, so basically R is some fraction between -1 and 1, the series is guaranteed to converge. The terms are getting smaller fast enough for the sum to level off. But if the absolute value of R is 1 or bigger, the terms aren't shrinking and the series will always diverge. That's it. It's really that simple.
And here's the best part. If you know it converges, you get the ultimate prize. You can find the exact sum, the infinite sum, instantly with this ridiculously simple formula. The sum S is just the first term, A, divided by 1 minus R. That is it. No more adding forever. Just plug in two numbers and boom, a perfect finite answer.
Okay, so geometric series are awesome. We've got a great tool for them. But what about all the other kinds of series out there? Well, there's one more test we're going to look at today. Think of it like a quick first look, a basic check you can run on any series you come across.
This is called the nth term test. And really, it's just common sense. Think about it for a second. If you're going to keep adding numbers forever and ever, and those numbers you're adding aren't getting smaller and heading towards zero, is there any chance the total sum is going to stay finite? No way. If the terms you're adding don't eventually shrink to nothing, the sum is just going to blow up. The series has to diverge.
Now listen up, because this is the most important thing to get about this test. It's a one-way street. It can only prove a series diverges. That's it. If the terms do go to zero, the test tells you absolutely nothing. It's inconclusive. It just means, okay, this series might converge, but you're going to need a bigger, better test to find out for sure. All right, let's look at a few examples here. First one, the sum of 2 to the n. Well, the terms are just getting bigger and bigger, right? The limit is definitely not 0, so diverges. Easy. Second one, the terms are getting closer and closer to 1/2. Still not 0, so that one also diverges. But now look at this last one, the famous harmonic series. The terms, 1 over n, they do go to 0. So does it converge? Well, according to this test, we have no clue. It's inconclusive.
And that really brings us to our final thought for today. We've seen that adding forever can give you a finite number, thanks to the idea of convergence. We've got a fantastic shortcut for geometric series, and now we have a quick first-pass test for divergence. But what about a series like that last one, where the terms go to 0, but its fate is still a mystery? So, what comes next? What other tools are in the toolbox? Well, that is where the real adventure of infinite series truly begins.